Testing 1, 2, 3. All right. Just make sure I've got some screenwriting here. There we do. Okay. So my name is EJ Daigle again, the Dean of Robotics and Manufacturing at Dunwoody College, and I'm going to do a few, or at least talk a little bit about analog inputs and outputs, a little more specific to the S7-1200 Siemens PLC, but much of this can be adapted to any analog I/O in the world of programmable logic controllers. I will warn you ahead of time, some of the examples I'm going to do, at least one of the examples for sure, we're not going to get in depth on the mathematics. When you get into the real world, if we're talking about thermal properties and things like that, there may be a lot more that you have to take into consideration. But for the purpose of this example, it's going to help us with how we'd go about using the analog I/O. All right. So first off, let's talk a little bit about analog inputs. So analog inputs vary their resistance, causing voltage drops proportional to their measured values. This can then be measured using a PLC analog input. So as an example, let's say I have a 10-volt signal and I have some sort of variable resistance that's going to go to my PLC input here. And if it's an analog input, then what's going to happen is this could be, could be temperature, could be pressure, could be humidity, could be a number of different things that are causing this thing to have a voltage drop. But if its voltage drop varies between 0 and 10, that means the analog input voltage drop's going to, or the analog input screw terminal is going to see a difference between 0 and 10 volts. So as an example, if this is at 5 volts because it's at 50 degrees Celsius, then my analog input is going to be at 5 volts. And if this is at 0 volts because it's at 0 degrees Celsius, then the analog input is going to be at 10 volts because I have to consume this 10 volts between these two loads. So things like thermistors and flow meters and pressure sensors, transducers, temperature sensors, relative humidity probes, all of these things are going to utilize analog inputs. I guess I didn't mention here, but analog outputs are going to be very, very similar, right? Analog outputs might include things like three-way mixing valves, might include things like linear proportional controllers, speed controllers, damper positions, things like that. So those are some analog output examples you might see as well. When we get into the lab with the S7-1200, we have one analog output. I don't have a picture of it over here, but if you remember on your PLC, the actual PLC CPU has a signal board that's right here. And that signal board is our analog output. That analog output is a 0 to 10 volt DC output, and it's going to be referenced as QW64 in your PLC code. On the input side, we have two analog inputs, and these two analog inputs are kind of up in this area of the CPU module itself. They are 0 to 10 volt DC inputs, and you'll notice that they are referenced as IW64 and IW66. Part of the reason why we start out at the 64 word address is the first, 8 expansion modules or so, or how many expansion modules output addresses are reserved for expansion modules. So I can take expansion modules out, and out. And if this is, I0 and I1, this one's going to consume I2, and this one's going to consume I3, and maybe Q2 or something like that. So I'm going to get out far enough that eventually I'm going to run out of the need for expansion. And so they put these analog addresses way out beyond what the expansion modules would be. But it's also worth noting that these input and output modules, this could be a digital in, right? But this could also be an analog in. This could be an analog out. So you can do expansion modules with analog input and output, just like you could with digital inputs and digital outputs. So how does the S7-1200 analog input work? So you can see how they show a diagram here, M being your 0 volt common, or your midpoint, as we would call it. We supply a varying voltage, typically from 0 to 10 volts DC, to this analog input screw terminal AI0. That AI0 address is then referenced in the code with the address IW64. Now, right off the bat, by this point in the curriculum, as soon as I show a W in here, everyone in the class should be thinking the a 16-bit word. And for most of us, I think, remembering back to Alan Bradley and Ars Logix, we're going to think, well, integer, word, integer, 16-bit. We're going to think, oh, 0 to 32, 767. You're definitely thinking along the right lines by doing that. It's worth noting that these analog inputs that we're talking about, they are read-only values, where we would call an analog output a write-only value. Analog inputs are read-only. It doesn't mean that you can't see what they are, or you can't, affect them, but the PLC is going to read them based on the voltage. If you want to change what they're reading, you're going to have to actually physically change the field device. What the measured value is that the field device is seeing. And it'd be the same with analog outputs as well too. It's some important notes here. Ensure if you're tagging these analog inputs, you will want to tag them as integers and addressed at the word level. So if I create analog input 0, first of all, I got to make sure it's on IW64. We've already told you that. You better make sure it's also the data type of an integer. Okay. Some differences from maybe the Ars Logix platform. You'll see that the what I got here, AW64, this should really be IW64, right? IW64 full scale range. What you're going to see on this is that full scale, 0 to 10 volts DC, we actually only get a word from 0 to 2764. Now what Siemens has done is they've provided what we would call some overshoot and some overflow. A lot of times you might be dealing with a 12 volt DC power supply. And we're really only concerned with 0 to 10 volts DC, but rather than letting a signal bigger than 10 volts cause an error, or letting it wrap around into, let's say, negative 32,768 or something like that, what they've done is they said, well, we're going to scale 0 to 10 volts from 0 to 27,648. And then if it goes over that value, we call that overshoot, but we'll scale that as well. And if we go over that value, it's called overflow, and we're going to scale that value as well. So we're going to try to stay within this 0 to 27,648. But we also know that if it goes over that a little bit, we're not going to flip around to a negative number, or we're not going to get an error or anything like that. So it's not near as bad as it potentially could be. So if we were to look at these now and say, okay, well, 0, what is 0? Well, 0 is going to give me a 0, right? So I always like to draw it with 5 zeros, because we got 5 digits all the way down here or whatever. 10 volts DC is going to go to 27,648. Now the question is, what does 11,110 go to? Well, if we know that 10 volts goes to 27,648, and we set that equal to some value in voltage that we don't know, X, and we want to set that to 11,110, we can real quick and easy, I'll keep my well, yeah, I guess I'll keep my math here for a second. It'd be real quick and easy to go into my calculator here and say, well, 10 times 11,110, and divide that by 27,648. If you didn't catch what I did there, really all I did was I did a cross multiplication over here on the 10 times 11,110 and 27,648 times X. And the number I got out of that 10 times 110, I divided it by 27,648, and I came up with this 4.02 is essentially what I came up with for a voltage there. And so I will write that in here as 4.02 volts DC. And now you can always kind of do a gut check and say, well, I wonder if that's right. Well, if 27,648 is full scale, then I'm going to guess half scale is what? Is it close to 14,000, right? So I would expect this to be, if 28,000 was full scale, half scale or 5 volts would be at 14,000. So I'm expecting it to be a little less than 14,000. That looks like it's a reasonable number. If I do this 6.9, I do it a little bit different now. Instead of this being the X, now it's 10 over 27,648 is equal to, I've got 6.9 volts over some value X for the analog word. So we'll do that one real quick here too. And we'll say, okay, a little bit different math. So 27,648 cross multiplied to 6.9 gives me that number. I'm going to divide that by 10. I get 19,077. Interesting note here, 19,077. I'm not going to keep that decimal place. I got a bad habit of sometimes truncating when I should be rounding. It will round it. But now I want to do that gut check again, right? I said, if this was 28,000 is full scale, then half is 14. About 7 volts should be a bit more than 14,000. Gut check complete. I feel like everything's good. So these are kind of your two equations, you know, equation 1 and equation 2 to kind of do through these math. So I'll leave these last couple here that you guys can kind of try on your own and make sure that you have those down cold. Let me keep those annotations for now. Go back in here. So again, back to analog inputs. What are some of these analog inputs that we can see? You know, a temperature probe, sure, absolutely. A thermistor, an RTD, or any type of temperature measuring device. What we're actually seeing here, it appears, is would be a motor shaft of some sort. I can see the keyway on this motor shaft, and I can see a tachometer. Now, this isn't hooked up to a PLC, of course, but what we're doing is as the motor shaft is spinning, we are measuring the RPMs in that motor shaft. Well, I can also use encoders and other things as analog inputs. If it's truly a tachometer, some tachometers will measure the RPM, convert it to a 0 to 10 volt signal, and send it into the PLC as a 0 to 10 volt signal. That would be a true analog input. If you're using a digital encoder, it's no longer an analog input. The data has been digitized. Flow meters, you may see a pipe leading up to a flow meter. Sometimes these flow meters, you have a liquid going through a tube, and this flow meter a lot of times will have a little wheel in it. And as the liquid flows past that wheel, the wheel will spin around in here, kind of like this, and then it'll send out a 0 to 10 volt signal that is proportional to the rate at which the wheel is spinning around. So my easiest math would be what? 0 gallons per minute gives me 0 volts DC, and 100 gallons per minute gives me 10 volts DC. But there are different ranges and different scaling, and Omega is a company that makes a lot of these types of flow meters, and Omega also makes a lot of pressure sensors as well. So I can measure 0 to 100 psi, and I can put a sensor in a tank or a pressure vessel, and I can send out a 0 to 10 volt signal. Relative humidity, light sensors, all kinds of different devices there. On the analog output side, one of the most common things we do is we do speed control. We might send a 0 to 10 volt signal over to a VFD or to a DC drive. And those drives then will convert it to a speed and drive a motor. I might send it to a temperature controller, a PropCon, or a proportional controller, and I send a 0 to 10 volt signal there, and that's going to determine the duty cycle for my heater or something like that. I might send it to a three-way mixing valve. Three-way mixing valve is hot water on one side, cold water on one side, and it mixes it inside of a three-way mixing valve to send out a mixed value. I might want to control a damper position. So I have an airflow, and I want to control or throttle the amount of airflow or something like that. So these would all be analog. The thing to think about analog inputs and outputs is always think of they are not on and off. They are zero. I think of them as 0 to 100%. If this is cold, this is hot. But if I want warm, I just put it right in the middle, right? It's kind of like when you're taking a shower in the morning. You got to throw a mixing valve in some showers. You don't set it all the way to hot. You don't set it all the way to cold. You set it some way in the middle. And that would lead me into my next example here. So let's take a look at this. This is a three-way mixing valve example. You'll notice in this tank here, I have hot water at 180 degrees Fahrenheit. And in this tank here, I have cold water at 40 degrees Fahrenheit. So you might think this is in a water heater, right? I've got a heater that's supplying this hot water, and maybe I have a chiller that's supplying this cold water. Well, these two waters can be piped into what's called a three-way mixing valve. And the way the three-way mixing valve works is inside this three-way mixing valve, there's a little gate. And if the gate's right in the middle, it's at 50%, and I get 50% cold and 50% hot, and that becomes my mix. But what I know is that I know that little gate can swing that way or can swing that way, and depending on which way it swings determines if I get less hot and more cold, or more hot and less cold, depending on the way it swings. So I'm going to pretend for a minute that if if I send a 0 volt signal from the PLC, so let's say my PLC can send a 0 to 10 volt signal, it's going to send it to this three-way mixing valve and position that gate. If it sends it a 0 volt signal, I'm going to get 0% hot and 100% cold. So my water coming out is going to be 40 degrees Fahrenheit. If I send it 2.5 volts, I'm going to get 25%. So you can imagine this gate is starting to go this way now a little bit, right? I'm going to get 25% hot and 75% cold. So now I'm going to get 25% hot water, right? There's some mix there that I'm going to get. If I send it to at 5 volts DC, that should be pretty easy. That's a 50-50. So 50% hot, 50% cold. And if 180 to 40 is 140 degrees difference, between these two, that's 140 degrees, then I know it's 70 degrees is the halfway point. So 70 plus 40 would give me 110 degree water. So my water coming out would be 110 degrees, where up here it was 40 degrees because it was 100% cold. And then if I send it 90% hot and only 10% cold, now the water is going to be very, very hot coming out. I would venture to say it's probably going to be 10% less than 180 degrees. Now this is where I want to remind you, this isn't a thermodynamics lesson. This is a lesson on just trying to figure out, how do these analog inputs and outputs work? How does the PLC do this? There may be some scaling, there may be some calibration that you have to do to actually get this to work. And then the other thing to remind you that's different than maybe some of the other PLC background is our analog word is 0 to 27648. So it is not actually a number from 0 to 32767. So when we did those calculations, you'll remember we did them all based upon 27648 when we were doing our calculations here. So that's important. All right, so now what we're going to do is we're going to do this hot-cold mix, and we're going to kind of find out, I got to remember a few things here, right? I got to remember that 0 to 10 volts is 0 to 27648. That's important for me to remember. So I can determine what my analog output should be. So in this case, the PLC, maybe there's an HMI where I type in the temp I want, right? And that goes over to the PLC. The PLC does some calculations, and then it sends out an analog output from 0 to 10 volts. I'm going to call that analog output QW64. So you're going to have to do some calculations inside the PLC to determine what voltage you want to send out to get this output mix. So we've got hot water, and we've got cold water, and when I mix the red and blue, I get an output mix of this purple water, right? And we're going to assume, for the sake of argument for this particular example, we're just going to leave the temperatures alone. It's possible on the worksheet I might actually change. Is it possible in the real world that that your hot water temperature may be a little low one day? Maybe your hot water heater over time, this year it's pumping out 180 degrees of water and it's perfect, and next year it's only pumping out 178 degree water. Those are things you may want to take into consideration. So you may want some feedback from your water heater and your water chiller as far to the PLC to monitor those and know what they're at, right? And then 40 degrees F. So if my desired temperature, as an example, for my output was, let's say, let's pick a number somewhere in between, not halfway in between probably. Let's pick kind of a low number. Let's say 70 degrees F. I want this number coming out to be 70 F. So what am I going to do? Well, what I would do is I'd look at the number line here, and I'd say, well, here's 180 degrees and here's 40 degrees. And I know that there's 140 degrees difference between those two, right? So from here to here is 140 degrees, between my hot and my cold water, right? So I got to figure out, well, maybe where is 70 in the scale, right? So what I would do is I'd say, well, 70 is 30 degrees above the minimum, right? And so where is 30 with respect to 140? I might say, well, let's see where 30 is with respect to 140. Let's get a number on that. So I'll hit escape here, and I'll keep my annotations so we don't lose them here. And I'll say 30 divided by 140. Looks like that's going to be 0.2143 or something like that. So that gives me 0.2143. 0.2143 is my number. Now, what does that mean? Well, it means you're at 21% of the full scale. If you divide this up and say that this is 50%, this is 75, and this is 20%, 21% is somewhere, 25%, 21% is somewhere around here. So all you really have to do at that point is just take that 0.2143 and you're going to multiply that by your 27,648 and you're going to get a number. And so I'll keep those annotations again. So I'll take 0.2143, which is still in my calculator here, and I'll multiply it by 27,648, and I get a number of 5,924 is what it looks like. And let me just look at that again. 5,924.57. So I'm going to say 5,925. I'm going to go ahead and round it up and say 5,925. So I'm going to say that that is my output word, 5,925. And you're like, okay, well, what does that actually mean? Well, what it means is, it means that I'm not at zero, right? At zero, I'd be pumping out 40 degrees water. And halfway at about 14,000, which would be like right here, right? 14,000, if this was, we just kind of ballpark it at this is 28,000 for the analog word, then this would be like 7,000, right? If I wanted exactly 25%. But at 21.43%, I'm going to pump out 5,925. That is my analog word, 5925, that I need to send out to get the desired voltage, which is going to be, 21.43% of 10 volts, which is going to be 2.14 volts, to get the desired valve position, which is going to be 21.43% open. So what that means is that 21.43, that means that I have 21% hot water and I have 79% cold water. Well, does that make sense? Absolutely it does. 70 degrees is a lot closer to the cold water value than it is to the hot water value, right? Let me change my pen color here for a second just so we can do this next one here and not lose track of which one we're looking at. So ink color, I'll pick kind of a bluish purple here. And let's pick a different temperature. Let's pick something like 150 degrees Fahrenheit. I should have done these backwards, but that's fine. Where is 150 in this range now? Well, 150 is a heck of a lot closer up here, isn't it? If this was, I think this number here was 110. So now I got 70, so this would be like 145, yeah, something like that. So I'm expecting it to be like close to maybe a little more than 75%. So I'll do the exact same thing. I'll say I want 150. Well, where is 150? So 150 above 40, so it's what is that? 110 degrees. It's 110 out of the 140 max I can get because it's 110 degrees above the 40 minimum, right? So I need to increase that cold water by 110 degrees. So 110 divided by 140. Let's take a look. 110 divided by 140. I get a 0.7857. 0.7857. That's going to be this number right here. Lost my marker color, 0.7857. Pointer options, color, get my blue again. All right, 0.7857. So what it's telling me is it wants the valve to be 78.57% open, which means it's going to be, way over here. It's going to be a lot of hot water, 3/4 hot water and only, a little bit of cold water. So 78.57 is a lot of hot water. Well, does that make sense? Sure. 75% would be right here. 78% is a little bit more because I need to get up to 150, right? Now I need to know what that analog word though is, 0.7857. So I'm going to go into here and take 0.7857 and I'm going to multiply that by 27,648 and I get 21,723. 21,723. Get my pointer color here again. 21,723. 21,723. 21,723. So that would be the analog word I would send out, 21,723, to get 78% hot and only 22% cold. Now again, we're not taking into account anything. You know, the ambient temperature of the pipes, the response time of the valve, any of this other stuff. We're not getting any feedback from the system. We're just giving it a good ballpark for how these analog values could play into doing a three-way mix. Again, the analog output device being this nice little three-way mixing valve right here. And if I send it the 10-volt signal, guess what? I'm going to assume for the sake of argument in this case that I'm getting 180-degree water out of there. However, if I send it a 0-volt signal, I'm going to assume my water temperature coming out is going to be 40 degrees. The reason being, again, is if you look at that valve, the way that valve looks internal to it, here's where my out's going to come. Internal to it, if I say this is 0% up here, and if this is 100% up here, and the hot comes in here, and the cold comes in here, and the out comes out over here, then I can see when my valve is at 0%, I'm completely blocking the hot water, and only cold water can go into that pipe, right? But I can also see if I flip that valve down, if I turn it all the way down to 100%, only the hot water is going to go through. And it's only if I kind of go somewhere in the middle, right? It's only if I go somewhere in the middle that I end up with something that's kind of in the middle, right? So at 50%, I might end up with, half hot and half cold, right? So you can kind of see how that three-way mixing valve is going to help control the temperature of our output. So with that, I hope that helps you guys with the worksheet and the job in the lab for working on the analog systems. Again, EJ, Dunwoody College. I appreciate your time.